Hello everyone, welcome to Logistic Regression with Python application class. In this class, I will be using default data to show you how to apply logistic regression. I will illustrate the concept of logistic regression using a simulated dataset. And we will be interested in predicting whether an individual will default on his or her credit card payment on the basis of annual income and monthly credit card balance. Let's first import the libraries and then start importing the data. So these are going to be the libraries that I will be using. So I start importing them. Let's start our analysis by taking a look at the correlation of the variables. As you can see, default is positively correlated with balance, negatively correlated with income, and positively correlated with being a student or not. Now let's create some scatter plots to see the relationship between the variables. Okay, there are two charts here. The chart to the left shows the relationship between loan balance and default, and y-axis shows default and x-axis shows the loan balance. Y is equal to 0 means that the customer did not default, and y is equals to 1 means that the customer defaulted. So as you can see, the defaulted customers have the tendency to have a higher balance. Similarly, the chart to the right shows the relationship between default and income. This time, people who did not default seems to have a higher income, and people who defaulted seems to have a lower income. These are just some exploratory analyses. Now I'm going to draw a couple of box plots to explore the data from a different perspective. Since this is going to be a very long block, I'm going to copy and paste. Again, there are two box plots here. The one to the left shows the distribution of income with respect to default groups, and the right shows the distribution of loan balance with respect to default groups. On x-axis, we see the dummy variable default. So this one shows that the people defaulted, this one shows people did not default. As you can see, people who defaulted has on average less income, and people who did not default on average have higher income, which we expected before. When we look at the right chart, this is again what we have expected. People who defaulted seems to have higher balance. People who did not default seems to have lower balance. Okay, now let's take a look at the descriptive statistics of the data set. This was for the whole data set. Similarly, we can do the same thing for the two different data sets, namely default and non-default groups. And this is for the two groups. As you can see from the whole data set, we had 5,000 data. Now we have two groups. In the first group, defaulting group, we have 500 data. And then in the second group, we have 4,500 data. And all descriptive statistics are given here. Now let's run a logistic regression without train test split. And then I will do the same thing with train and test split. Okay, so this is the output of our first logistic regression in which we only used one variable, loan balance. I will use the other variables in a moment. And the other thing to note is I used the whole data set, 5,000 data points. I did not divide the data into train and test split. As you can see, the intercept is negative 7.73 and the loan balance coefficient is 0.0006. So if you want to estimate the probability of default for this customer, this is going to be our model. B0, which is the intercept, is negative 7.73 and slope is 0.006. So if you want to estimate the probability of default for a customer, say, who has loan balance of $10,000, the process is going to be substituting $10,000 instead of X. If you do the math, you will get 0.15, which is going to be the probability of default for this customer. We can also calculate and visualize the predictions as follows. So this is the ultimate situation of my estimation. So the blue points are the actual data and the red points are the values that I predicted, I estimated. So for every single balance, I have a corresponding estimated probability of default, and there will be a cutoff. So let's assume that the cutoff is 0.5. This means that all of the predicted values beyond that cutoff point, which means these values, are going to be assumed to be defaulting, and all of the predicted values below this point, which means more or less people whose loan balance is less than $10,000, are assumed to be non-defaulting. And now let's add the other two variables, income and student, and run the logistic regression with all the variables. So I use all of the predictors, income, balance, and dummy variable. And number of observations, 5,000 people. So I did not use any train and test split. There is a measure called pseudo R-square in logistic regression. This measure approximates how well our model explains the variability in the outcome, similar to R-square in linear regression. But they are not one-to-one comparable. Therefore, I will be checking the confusion metrics to compare my model with the rest of the regression I will use in this class. So since the code is a little long, I'm going to copy and paste it here. So it gives me the confusion matrix and the accuracy score. As you can see, the accuracy score is almost 94%, which is quite high. As you will see in a moment, that the model with train test split will give the same accuracy score. Now I'm going to do same analysis with train and test split, dividing the data from 60%. So 60% of the data is going to be my train set, and 40% of the data is going to be my test set. So this is going to be my y variable, which is the target that I'm explaining. The explanatory variables, which is the matrix X, is composed of all the columns except the default column. So now let's write the code for train and test split. So this is train test split. Run this. The code is working. Now I'm going to run the logistic regression for my dataset. Okay, so these are the intercept and the slope coefficients of my model. Let's take a look at the predictive performance of my model. As you can see, the overall performance of my model is almost perfect. It is mainly because this data is a simulated data set. So now let's take a look at the confusion matrix. So the first row refers to actual non-defaults and the second row refers to actual defaults. So I'm going to draw a colorful confusion matrix here. So what I'm going to do is just copy paste a very long code just to illustrate the situation. As you can see, the first row shows us the actual non-defaults and the second row shows us the actual defaults. So out of 1,807, I have 1,793 actual non-default predictions. And out of 193 defaults in the second row, I correctly predicted 89. So if we add our two correct predictions, which is 1,793 plus 89 divided by the whole sample, which is 2,000, gives us 94% correct predictions, which is accuracy. And this shows us our prediction performance. Okay, in this video we reviewed how to run logistic regression where output variable is binary. I hope you enjoyed the video. See you in the next videos. Bye.